although I'm not sure that's possible because it's just a complicated topic. When last we left, we had looked at our shells, our subshells, and our orbitals, yes? So in our first shell, this is the n equals 1 shell, we have a single subshell. This is the 1s subshell, and it contains only one orbital, the 1s orbital. In our second shell, n equals 2, we have the s orbital. So this right here is the 2s subshell, and we have the 2p subshell, which is made out of 3 individual p orbitals, one going top to bottom, one going front and back, and one going left to right. Yes? Now, what if we were to take all of these and overlap them so it looks like what it would look like in the atom? It would look something like this. Wow. Yes? Do you need to know what that looks like? No, not really. You just need to get the idea that they do overlap and just be okay with that. They overlap, but they never touch, okay? Which I know. It's because the electron is just a particle, but it's also a wave. Can a wave like overlap but not touch? Yes, because it's a wave. Waves don't touch because they're not particles, but it is a particle, but it's not, okay? So just let it go. Just be like, okay. Similarly, we can do the same thing for our d orbitals. We can show what they all look like together. Okay, so we have 1, 2, 3, 4, 5 d orbitals. So this would be a d subshell. So this is the 3d subshell. And then this is 5. And then this is all of them overlapping. Not that you need to be able to draw that or even visualize it. It's just kind of like, there we are. So you've at least seen it. Okay. On our next page, we have our 1s orbital. You can see it's here, but it is overlapping with the 2s and the 3s, and we'll take a closer look at those orbitals. And do you see how we have some areas where there's not very much electron density, right, where it's white? And we have some areas where we have high electron density. But basically, if you have an atom, all of those exist and they just exist one on top of the other. And if we decide then to throw together here's our 3s right here. Here's our 2p's. Okay, and then we have our 2s here. And then we have our 1s way in here. And they're just all overlapping. I don't know why I got so excited about drawing the overlapping things. Because like I said, you don't really need to know this. And then let's throw in a 3p for fun. There it is. Yay. There's some exercises which I will let you do later as part of your homework. Okay, so that's pages 80 and 81. And now we're on to 9.3e, which is on page 82. So an energy level which is also known as a shell, contains one or more sublevels. At this point, I feel like we should know this. Do we know this? Okay. Now, a sublevel, or a subshell, contains one or more orbitals. Do we know this? Yes. Okay, good. And each orbital can contain a maximum of how many electrons? 2. Okay. So let's take a look at a set. We have here, this is the n equals 2 energy level. So this is energy level 2, which is also known as shell 2. And within that energy level, we have the 2s subshell, and we have the 2p subshell. Also known as sublevels. And then within the 2s subshell, we just have the one orbital. But within the 2p subshell, we have an orbital, and an orbital. And because drawing those gets to be a pain in the butt, we can substitute that by drawing the 2s orbital, and then we can draw the 3 2p orbitals. So we're taking this complicated thing and we're simplifying it down to just little boxes. Yes? And this entire thing together makes up the shell. Subshell, subshell, shell. Now we're going to talk about 2 different types of atoms today. We're going to talk about atoms that have only 1 electron in them. Who is the only atom that has only 1 electron in it?
Hydrogen.
Hydrogen. So hydrogen is in a category by itself, okay? Because it is the only single electron atom. If you only have 1 electron, will that electron ever experience electron-electron repulsion? No, because it cannot repel itself. That makes no sense, yes? So, the 1 electron cannot experience electron-electron repulsion. And this has a consequence that makes hydrogen different from everybody else on the periodic table. And what that is that if we look at all our energy levels in terms of where they sit with the amount of energy in each of them, everything in energy level 4, the 4s subshell, the 4p subshell, the 4d, the 4f, all those subshells have the same energy. And the reason they have the same energy is because there is no electron-electron repulsion. It is electron-electron repulsion that makes the electrons in different subshells kind of repel each other differently and bump things to higher energy levels. Okay, so what's happening here is we have all these subshells in n equals 4 have equal energy. All the subshells in n equals 3 all have equal energy. All the subshells in unit in n equals 2 have equal energy. And we're going to learn a new word now. That word is degenerate. You may have learned this in another context. I always think it makes, if we say the orbitals are degenerate, it makes them sound like they're out drinking and smoking and, just generally behaving badly. But that's not the meaning of degenerate here. That's what degenerate means in sort of a social context. But degenerate means of the same energy. So in hydrogen, all the orbitals in an entire shell are degenerate. Okay, so in hydrogen, which has only one electron and has no electron repulsion, all the orbitals in a shell have the same energy, which means that all the orbitals in a shell are degenerate. So far, so good? Okay. Now, if you're thinking, hey, hang on, this weekend when I did my homework, did everybody do their homework? Good. They didn't have all the n equals 3s at the same energy. They were like up and down, and you know what I mean? So that is because this is for hydrogen only, okay? Multi-electron atoms, this is everything except hydrogen. If you have more than one electron, electrons can repel one another. So all the orbitals in an energy level are not degenerate. So what happens is, if you have more than one electron, the electrons repel each other. And the consequence of that repulsion is that if you have an orbital of a different shape, so if we have orbitals of different shapes, they will have different energies. So an S, which is sphere-shaped, will have a different energy from a P, which is peanut-shaped. Okay, both in energy level 2, but they would have different energies. Not completely different, like they're not like really far from one another, they're still fairly close, but one is higher than the other. So 2s is lower than 2p. So in a multi-electron atom, each subshell has a different amount of energy, but the orbitals within a subshell are degenerate. So you can see here on the side, again, we have increasing energy. Okay, so as we go up, the energy increases. And if we look at all the 7p orbitals, all the 7p orbitals have the same energy. right? They're not higher or lower than one another. Okay? What that means is that therefore they are, what's that new word we learned?
Degenerate.
Degenerate. And you can see whatever subshell you're in, the 5D, all of those orbitals are degenerate. But they're different from the 5F. Yeah, 5F is different than the 5D. Now, wouldn't it be nice if everything went 1S and then 2S, 2P, and then 3S, 3P, 3D? Wouldn't that be nice if those were the energy levels? Like how they went up energetically? But that's not how they go up. They go up 1S. That makes sense. That's the lowest energy. Then we have 2S and 2P. That makes sense. So far, so good. And then we have, yes, potential energy. Good question. Okay. And we're all good. 1S, 2S, 2P, 3S, 3P. We're really good up to 3S, 3P. But if life were making an entire amount of sense, then the 3S and the 3P and the 3ED, which are all in the same shell, this is shell number 3, n equals 3. We can call it energy level 3. But who's energetically kind of stuffed itself in the middle there? For S slots in before the 3D. Okay? The way I like to think about it, this is how I've always thought about it, is the D orbitals, they're like the ones that have the, the 4 little lobes, right? And I'm thinking if I were an electron and I just was living by myself in an orbital or with one person in an orbital, would I want to have like 4 things where I had to like move here and move there and be all complicated and whatever? Or would I just like to sit in a nice cushy sphere? Yeah? As an electron, I'm thinking a nice cushy sphere would be just more comfy. Yeah? Which is why it brings it down to a lower energy level. That's not the actual reason why. The actual reason why is that S orbitals have a lot more electron density close to the nucleus. And so even though the outer portion might, if you're at like a 3, if you're at a 4S, the outer portion of it might be quite far from the nucleus, but most of the density is still quite close to the nucleus. So it's still at a lower energy than the D, because the D, if we think about an S orbital, it's a sphere with its density closest to the nucleus, okay? And then it sort of gets more diffuse as you move outwards, okay? But a D, does it have a lot of density close to the nucleus? No, right? It's got a lot of empty gaps close to the nucleus. So that's the real reason why. But I always just think that, as an electron, it would just be nicer to hang out in a nice squashy S orbital as opposed to a complicated D orbital. And that's why the Ds are higher energy than the S's. The S's are just so nice and comfy that they slot in at a lower energy. And I did want to mention, because it confused my period 2 class, Watch out for the difference between energy level and the amount of energy. Yeah? Because these three guys here make one energy level, these three subshells, but each subshell is at a different potential energy. So when we say energy level, we mean the N value. Okay, energy level means the N value, not the actual potential energy. Because, of course, we've got three different potential energies within that energy level, right? And then we've got 4 inserting itself in between those, and it's all crazy, right? But really, what you should take away from this diagram is that this applies to all atoms that are not hydrogen, and it's always the same, okay? The energies are the same, and that the orbitals in a subshell are degenerate, okay? So the orbitals in a subshell are degenerate. So the P is the same as a P is the same as a P. You must memorize this diagram, but not really. Okay, because all you need to know is the order. Yeah? Because an electron, when it has a choice, where is your first electron going to go? It's going to go in the 1s. Where's the second electron going to go? In the 1s until you filled up the 1s, and then the third one, and then the fourth one, and then the fifth. Where does the sixth one go? 6, 7, or sorry, 1, 2, 3, 4, 5, 6, 7, and they all point the same direction until we start doubling up, and then they have to point opposite directions. Okay, so we got 4, 5, 6, 7, 8, 9, 10 electrons, and then 11, 12, 13, 14, 15, 16, 17, 18, and then 19 goes into the 4s. Okay, so that's the order of filling. So you don't actually need to memorize this chart. I mean, if you wanted to, you could go home and draw it out 17 times. Or you could say, I need to know that 1s is at the bottom, and I need to know that 2s is above that, and 2p is above that. I need to know the order going upwards. Yeah? And in order to know that, you can use 2 different ways to remember it without drawing that diagram and just brute force memorizing it. Did you, on the weekend, learn the diagonal method? Yes? One thing to remember with the diagonal method is that you need to have your things lined up properly. Okay, I did it really well because I did it on a computer, which has, actual spacing on it. When I write it by hand, I have to be careful not to be like, 1s, and I can't do 2s over here, right? 2p, because then that's going to throw everything out of alignment and it won't work. Okay, so the s's all have to line up, the p's all have to line up, the d's and the f's all have to line up, and then energy level 1 is in the first line, energy level 2 is the second line, etc. down the rows. Okay, and then you draw your diagonal line. 1s, 2s, 2p, 3s, 3p, and it would be tempting to say 3d, but what comes after 3p? 4s. Okay, so that's going to get you the correct order. All right? And it'll give you all the other like weird exceptions and things like that too. So that will tell you the order in which the orbitals get filled. Okay? This is the order of filling the orbitals. So the order of filling is the same as the order of energy from low to high. Now, the downside of this is you got to draw out this stupid little chart, right? So I'm like, wouldn't it be nice if I could do this without having to draw anything and I could just read it off a page that I already have? And guess what I always have on me in a chemistry exam? I always have a periodic table. Yeah? So if I look at period 1, when I'm in period 1, hydrogen has 1 electron in its 1s subshell, and helium has 2 electrons in its 1s subshell, and then the 1s subshell is full. The n equals 1 is full. Yes, energy level 1 is full. So basically, as we're going across row 1, we are filling up the 1s subshell. 2s, over here, I'm just drawing the last electron, okay? Lithium has 1 electron in the 2s subshell, and beryllium has 2 electrons in the 2s subshell. And then the 2s subshell is full. Yeah? So what do I need to start on after the 2s? I need to start on the 2p. And we call this block here, this red block, the S block. And if you have an element in the S block, its last electron will be an S electron. So you'll have either a 1s1 or a 1s2 or a 2s1 or a 2s2 or a whatever S1 or whatever S2, okay? That's going to be the last electron. If we're over in the P block, like let's say we had boron, right? Boron would have its 2p subshell. Boron would look like that, and that would be 2p1, right? And we go across filling up 2p2, 2p3, 2p4, 2p5, and when we get over to neon, neon is going to be 2p6. We have filled up all 6. So neon would look like this. I got to write them really small. La, 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 la. Okay? Full. But anywhere you're in the P block, these ones here are called the P block, the last electrons are going to be something P. Okay, so 2p1, 2p2, 2p3, 2p4, 2p5, 2p6, or any of the other energy levels. Like if you're in the 4p, your last electron will be in the 4p block. Okay. These guys here, guess what they're called? That's called the D block. And the last electrons go into the D block. What do you notice about the Ds, though? As we go across period 1, we had the 1s subshell. As we go across period 2, we have the 2s and the 2p. And 3 has 3s and 3p. Uh-oh, why is the 3D not there? Because it's actually higher in energy than the 4s. So the fourth period contains 4s, 3d, and 4p. The Ds always lag 1 behind their row number, okay? So if you're in row 4, your d orbitals are 3d. If you're in row 6, your d orbitals are, if you're in row 6, your d orbitals are 5d, okay? Now, the F's are kind of weird because they get chopped out. And we're just going to pop to the next page because this shows you where the F block would actually go. So the F block lags 2 behind the row number. So if we are in row 6, it's a 6S, that makes sense. But then we hit the F's, and that's not a 6F, it's a 4F. And then the D block lags 1 behind the row number. So period 6 goes 6, 4, 5, 6. Period 7 goes 7, 5, 6, 7. S, FDP. S, FDP. Okay? And what that means is that when you are writing an electron configuration, let's say we went to this element here, right? We would say, okay, this is going to be a big long one. I have 1s and it's filled with 2 electrons. So I would have 1s, whoops, 2. 2s filled with 2. How many fills the 2p? 6. 2p, 6. Do you guys feel good about writing a configuration like this? Is that a skill you're feeling okay about? Thumbs up, thumbs down, thumbs in the middle. Okay, mostly thumbs up. Okay, I'll just do this one and then we'll go. So we got 2p6 and then we hit the 3s. So we have 3s. S's can contain only 2. And then we get to 3p and p's can contain 6. And then 4s can contain 2. And then, oh, I'm in row 4. So now I hit the 3 Ds. And remember, how many d orbitals? 5. So therefore it can contain 10 electrons. So 3D, 10. And then 4p, 6. 5s, 2. 4d, 10. 5p, 6. Good Lord, this is a long one. And then we hit 6s2, 6s2. And if I'm 2 along in here, then that's going to be 4f2. Whew. Exhausting. And if someone gave you that configuration, you'd be able to look and go, okay, it is 4f2. So you could look around and find where your F block is, where 4F is, and you could say, okay, I've got 2, so it'll be the second one along. Okay, that's all you have for that. So yeah, okay. Make sure that if you're not yet comfortable knowing these and that the F block slots in here, just grab your periodic table and start like pointing at a various row and place and just try saying which block you're in. Okay, right? And these ones go right here. And apparently there is an error in here. Did anyone else find the error? Someone found it in my first block. Where is it? Oh, it's right here. This should be 4F. The 4P after the 6S. 6S, it should be 4F. I need to fix that. Okay. This is the part that's really frustrating. This part. This one here. And I'm sorry, the name is unfortunate. It's called orbital penetration. What can I do? That's what it's called. So why do those different shaped orbitals have different energies, even though they're in the same energy level? Like, why are those two P's at a different energy than the two S? Well, Coulomb's law says the distance of an electron from the nucleus is important in determining the electron's energy. In essence, its attraction to the nucleus. How could we write a mathematical statement saying that the Coulombic force is proportional to, and have a little chit chat with your neighbor about what we should put on the other side? What mathematical sentence says the same thing as this word sentence, essentially, or at least close? Remember, the fish means is proportional to. Yes.
Are the like why is it for like the F block? Why is it 4 and 5?
Why is it 4 and 5? Because the F's are just really not accommodating of electrons. You remember how I said like the D's are uncomfortable? The D orbitals are uncomfortable. That's why the electron's like, ooh, a 4s is better than a 3d, because the D's are like complicated shaped. The F's are even more complicated shaped, so they're even less desirable. Yeah?
So it's just 4.
Yeah. I mean, honestly, that's probably all you're gonna get to at this point in your science career. Do you know what I mean?
Yeah.
Yeah.
I don't really get why it's 4 and 5.
You don't need to get why it's 4 and 5. You just need to be like, oh, they are behind. They are just at a higher energy because they are less comfortable for the electron. Okay? And the S's are more comfortable. And the P's are more comfortable.
Okay.
I don't really get it either because I don't really get waves. Like, it all comes down to math, and my math is not that good. Right? It's like all that, it's like 3D wave math. And I'm like, calculus, me, 2D calculus, maybe 30 years ago. But now, no. Okay, so what is the Coulombic force here? What would we say? Coulombic force is proportional to the distance, so it would look like that. So as distance increases, the force increases? No. As distance increases, the force increases. So, as distance decrease. Yeah, I'm just going to write it down because I'm not saying it, and I'm going to write it as an R because that's how it shows up on your formula sheet, and that's where R is the separation distance between charges. And it's not just 1 over R, it is 1 over R squared, okay? And if you forget that, where can you look? You can look on your pink sheet, yes? because it is on your pink sheet. Okay, and you can just, when you just want to talk about the R, you can just get rid of the Q's and you can say F, and on the exam I would write out coulombic. For us, I think writing FC is sufficient. Yes? But you could just say FC is proportional to 1 over R squared. Or you could say FC is proportional to Q. Right? You can take those out of that entire statement there. Okay? Okay. So now, orbitals in the same shell. Orbitals in the same shell. For example, 3s, 3p, 3d. They all have similar sizes and similar average distance of their electrons from the nucleus. So why do they have different energies? And this is actually going to answer your question, but you probably won't understand it because I don't really understand it, okay? Just letting you know, okay? And this is where, if you decide that 9.3F, you just want to throw that in the garbage after we've done it today, you're welcome to do so, okay? Chances of you being asked anything about this are slim to none, okay? This other factor, this other distance-related factor is known as, unfortunately named, penetration, which means, moving right along past that word, it is the ability of an electron to penetrate within other shells and subshells to get close to the nucleus. So you remember how they were all overlapping? You remember how we had the p orbital is like this? Yeah? S orbitals are like that. Do you see how this is kind of getting in closer? It's getting in between these electrons and the nucleus, which would be right here. The S, all the S electrons, which I'm going to do sort of in black, they are getting through the area where we have the p orbital and getting closer to the nucleus. Yes? And so that's why an S is at a lower energy than a P at the same energy level. Okay, so this would be like a 2S and a 2P. But they do overlap each other. It's just that the 2S can kind of get in there. And sometimes the 2P electron is here. And so it will experience repulsion by the 2S electron pushing it away from the nucleus at the same time as the nucleus is pulling it in. Yeah? And if you're like, then we'll just move on a little, right? Yeah? So the 2s electrons are almost shielding the 2p electrons from feeling the full charge of the nucleus, which is why they're at a higher energy level. How do we feel about that? Ish? Okay, we're going to go with ish. Okay, now, if you have a 3s orbital, it's going to be bigger, right? And its density is more spread out. There is some density right next to the nucleus for a 3s, but there's also some out here and some out here. So even though there is some within that nuclear range, like a 3s, and I know this diagram is going to get terrible, there is some 3s here, but the 3s would be like more out here and here. Okay, so it's not blocking as much because there's less of its density within there. Okay, now the amount that the electrons can penetrate towards the nucleus depends on, so the penetration depends on the energy level, the N value, and the shape of the orbital, the S, the P, the D, or the F. So S's, they have a very high electron density close to the nucleus. When we solve that wave equation for an S orbital, you remember that complicated equation that guy did all that math for? Okay. When we solve the wave equation, this is the probability field we get for a 1s orbital. This is the electron cloud. It is the probability field for 1s electron or electrons. I've done a terrible job of drawing a circle around that. That's supposed to be a circle, like an actual circle. It's looking more and more like an oblong every day, but there we go. Now, if you look at this, where do we see most of the little dots? Yeah, we have the most density. At the center, and we have the least density as we go further and further out. Now, technically, there is a boundary, but actually, technically, there's no boundary. But we say after you get to a certain distance from the nucleus, there is almost zero probability of finding an electron further than that distance. Now, it's non-zero. There could be an electron on the other side of the universe in that orbital, right? But it's extremely, 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 you're more likely to win the lottery than have that electron be the way the hell over there, okay? Now, 2s, do you see how 2s does have some density close to the nucleus? But then we have a node, and a node is where there is no electron density. Node for no electron density. There is a gap. So it's like there's a sphere, and then there's a hollow sphere around that sphere. And there's a gap between the small sphere and the bigger sphere with a little hole. And if you're like, I don't understand what that means, then you can just think of it like 2D, and you're like, oh, there's a circle, and then in between that, there is a bigger circle, but there's a little hole here. And so this part has stuff in it, this part has stuff in it, but this part has no stuff. And what do I mean by stuff? I mean electrons, okay? So you got electrons, no electrons, electrons. All right? And remember, nah, never mind. I don't know what I'm saying. It's okay. And then we have the 3s orbital, which is bigger still. It still does have density at the nucleus, but it has 2 nodes. Okay, it's got 3 sort of shells. What do they call them? Concentric shells. 3 concentric spheres, not shells, spheres. Okay? Yeah. It has to do with the fact that the electron is a wave. Okay, you remember the electron's a particle, but it's also a wave. And when waves interfere with each other, so if you get one wave going like this and another wave going like this, they cancel each other out. Okay, and so you'll end up, that's a point where they cancel each other out. And I'm so sorry if I'm killing anybody's physics teacher here, because I know that that was just a terrible explanation. Okay? Yeah. So, yeah. It's because they're waves and there's areas where the waves cancel out, and so there's nothing there. Okay? All right. Now we have these distribution graphs, which I'm sorry the text is a little bit fuzzy. What we have on our y-axis is the probability of finding an electron. And it's the probability of finding an electron at a particular distance from the nucleus, which is r, which is measured in A with the little 0. Do you remember what that stands for? Angstroms, which is 1 times 10 to the negative 10 meters. Okay, and r is the distance from electron to nucleus. And that's increasing from 0 angstroms to 1 to 2 to 3, all the way up to 10 angstroms. Yeah? What is our probability of finding an electron at 0 angstroms from the nucleus? In other words, right at the nucleus. What is the probability of finding an electron right there? It is 0. Yes? That's supposed to be a 0. It is some crazy symbol. Now, at about 0.5 angstroms, so the most probable distance is approximately 0.5 angstroms. That's where you are most likely to find an electron. And I'm going to rewrite this because it's so fuzzy I can't really read it. Most probable distance from nucleus. And you see, it's a very, very tall peak here, and it falls away very steeply. By the time we get to about 3 angstroms, we are virtually down to 0, right? So 3 angstroms is approximately the radius of the atom. Yes? But do you remember what I said? Does it go to actually 0? No. Even though this looks like it's at 0, it's approaching the line like this, yes, and it gets closer and closer and closer and closer and closer and closer, but it never touches. What do we call that? That's called an asymptote, yes? So if you've not heard of that before, we would say this line decreases asymptotically towards 0. Which is why we can say that, oh yeah, there is an incredibly small and yet non-zero probability of finding that electron on the other side of the universe. Yes? Even though it's really only 3 times 10 to the negative 10 meters across, that atom. So this one right here, this is a 1s orbital. Our second graph is a 2s orbital, and our third graph is a 3s orbital. Who has better nuclear penetration? A 1s, a 2s, or a 3s? Who has most density closest to the nucleus? The 1s. Yeah? So the 1s has the best orbital penetration. The most probable distance for a 2s is at about 3 angstroms. And the most probable distance for a 3s is about 7 angstroms. So who's getting closest to the nucleus on average? Those 1s electrons. Do you guys see the nodes? Are you able to relate this graph to that diagram? Right? Are we able to relate the 2s graph to that diagram? Right? Because we've got that node, we've got 2 blobs essentially in one node. Now, like I said, how much do you need to know of this? Right? And then we can do fun things like we can overlap them all and just show them all on one graph, right? Here's our 1s, here's our 2s, and here's our 3s. I feel like even though it's not on AP, I'm almost obliged to show this to you just because it might show up in first year. You know what I mean? And then if you've never seen it before, you're like, whoa, it's scary, right? Because this stuff is kind of like mind-blowing. But at least if you've seen it before, you won't be terrified. Now our p orbitals, we were talking about this before. The s has lots of density close to the nucleus. P orbital has much less electron density close to the nucleus. So who has greater nuclear penetration? The 1s. Yeah? So what could they possibly ask you that might actually use this? They might say, why is the 2s orbital lower in energy than the 2p subshell? And you could just say because the 2s subshell has greater orbital penetration. It gets, the electrons in there get closer on average to the nucleus. I don't think it's going to come up. Okay? Here's some pictures. Apparently, I like the word glonking. You can see there is a great glonking node at the nucleus for the p orbitals. There it is right there. Okay, there's our node. But you can see there's huge density instead for the s orbitals right at the nucleus. And just for fun, here's an overlap of the 1s, the 2s, and the 2p. La la la. And it's interesting to watch like the shape of the graph for the 1s and the 2s. The 1s goes basically straight up. The 2s goes straight up like this. And then the 2p, instead of going straight up, it kind of goes scoopy and then up. Yeah? And that's because it has that node area in there. Okay? And that's it for that. D orbitals have an even smaller penetration of the nucleus. You can see the Ds. Here's our D. It's essentially 0. Look at that. Yeah? Do we have a 4p? I would love to have a 4s on here and a 3d so that you could see like there with the 4p there or 4s, it's going to be like that's going to be like a 4s, and you see how it gets closer to the nucleus than the 3d, which is a terrible diagram, and I'm going to see if I can find one for you that doesn't look like that because that was garbage. Okay, la la la. How much do you need to know? Probably not much. And with that, we're kind of done. You guys did 9.3G. I asked my other class how many people had not done 9.3H. How many people have not done 9.3H? You guys have all done 9.3H? You are fantastic. Oh my God. Okay. At any rate, so we did go over a little bit of the core electron configurations. Would anyone like a review of the core electron configurations, or are we good? You would like a review? No, you're good. Okay. Anyone want a review? We're good. Fantastic. Yes.
Regarding the 9.3H.
Yeah.
Periodic table.
Yes.
Put carbon.
You're right, I did. It should be 1 over. Thank you. I will fix that. Yeah, I put carbon in the wrong place.
Yeah, but the answer was right. So
okay. Fix. You're like, why is carbon over there? That's not right. That's nitrogen. Okay.
I put 2p3 and it said it was wrong and I was right.
And you're like, what? Okay. At any rate, there we go. And that's it for that. And your homework is just a little extra practice on electron configurations. Okay, have been page 155, number 6. This is because there was a chunk of them that hadn't done it. And then 9.3E and 9.3D, that's just a little review of kind of what we did today. Okay, and tomorrow we're going to do electron configurations of ions and then kind of be done with 9.3.
How about you?